Hello friends, welcome to my channel SAK Electrical. I am your host Sikandar Ali Khan, and this channel is dedicated to electrical engineering concepts where you can understand the difficult concepts in an easy and interactive way. So the today's topic is the production of rotating magnetic field. So in this video we will see how a rotating magnetic field can be produced in a three-phase motor. So a rotating magnetic field is basically the big backbone of the working principle of both three-phase induction motor and three-phase synchronous motor. So without any delay, let us see how a three-phase system can be used for the production of the rotating magnetic field. Consider the statement: when a polyphase balanced current flows in a polyphase balanced winding, a uniform rotating magnetic field is produced. This statement is a general statement which is applicable to any number of phases, but for the three-phase system, this statement can be rewritten as: when three-phase balanced current flows in a three-phase balanced winding, a uniform rotating magnetic field is produced. So from this statement, you have some questions in your mind. First question might be, what is a three-phase balanced current? Another question may be, what is three-phase balanced winding? And you may have one more question, that what is a uniform rotating magnetic field? So let us first answer these questions and then we will move on to the qualitative analysis of a rotating magnetic field. So to answer these questions, let us first see what is a three-phase balanced winding. A three-phase balanced winding is that winding which has equal number of turns in each phase, and windings of three phases are space shifted by 120 degree. So there is a angular difference between the axis of different phases is 120 degree. On the other hand, three-phase balanced current is that current which has equal magnitude in all the three phases, and there is a phase difference of 120 degree between the currents of the different phases. So there is a space distribution of 120 degree in the winding, and there is a time distribution of 120 degree in the currents. So both of these conditions are required for the production of a rotating magnetic field. By the end of this video, you will know that if any of these conditions is not met, you will not have a rotating magnetic field. So before moving on to the understanding the concept of the rotating magnetic field, we have to have certain assumptions to ease our work. So the first assumption is that phase windings are assumed to be concentrated in opposite slots. Second assumption is the distribution of MMF and hence magnetic flux density is assumed to be sinusoidal over the air gap. Third assumption is, for the simplicity of representation, only stator is shown. And the last assumption is, for simplicity, a two-pole machine is considered. So if we consider all these four assumptions, the stator structure will look like this. So in this structure, you can see that the phase A winding is shown with red color, phase B winding is shown in yellow color, and phase C winding is shown in blue color. Now the same structure is redrawn here, but in two different ways. One is the circular structure and other one is the developed form. Here the slots are numbered from 1 to 6 in the clockwise direction. Now we will see that how the flux will behave when a particular phase winding is energized, and this will give the concept of the axis of a particular phase as far as the magnetic field is concerned. So let us say, let's see this with respect to the phase A first. So here you can see that the one coil side of phase A is placed in slot 1 and the other coil side is placed in slot 4. Now let us say the coil side which is placed in slot 1 is having a current which is coming out of the screen, and the coil side which is present in slot 4 is having the current which is going into the screen. Now we can apply the right hand rule to determine the direction of the magnetic field. According to right hand rule, the direction of the magnetic field is given by the curl of the fingers if the direction of current is given by the thumb. So if you place the thumb along the direction of current in slot 1, then the direction of magnetic flux is shown by the dotted circles with the arrow representing the direction of flux. Similarly, you can obtain the direction of flux for the current which is flowing in the coil side A dash. You can see that all the flux is in the direction from left to right. So basically the axis which is pointing from left to right is the axis of phase A winding, where the maximum amount of magnetic flux is lying. So red dotted arrow is representing the axis of phase A. Now in a similar fashion we can come to uh, we can come to the direction of phase B winding and phase C winding. So phase B winding is placed in slot 3 and slot 6. Let us say positive or outgoing current in slot 3 and the incoming current in slot 6. Depending upon these directions of current, the direction of the magnetic field for the two conductors or two coil sides is given like this, and based on this direction the axis of phase B winding can be shown with a dotted yellow line. So dotted yellow line is the axis of phase B. Similarly, phase C winding is placed in slot 2 and slot 5. Let us say the positive current is flowing in a coil side which is placed in slot 5, and the negative current is flowing in a coil side which is placed in slot 2. Depending upon these directions of currents, the magnetic flux or magnetic field can be given like this, and depending upon this magnetic field, the axis of phase C can be shown with the dotted blue arrow. The dotted blue arrow is representing the axis of phase C. Once the three axes are defined, these three axes can be shown on the actual diagram of the machine, and these axes can also be shown on the developed diagram of the machine. Now we will move in a step-by-step manner and we will see that how a three-phase rotating, the three-phase balance winding along with the three-phase balance current will be used for the production of rotating magnetic field. But first of all, we will have to see what will happen if a DC current will be applied to a particular phase winding. Let us consider a structure like this where the phase A winding is energized by a DC supply. The equation of MMF is given here, where the MMF of phase A is given as N small ia, where small ia is representing the instantaneous current. For DC supply, this instantaneous current will have a fixed magnitude and it is represented with capital IA. So FA is given as N capital IA angle 0, where angle 0 is representing the direction of the axis of phase A winding. So the axis of phase A winding is taken as a reference, and with respect to this all other angles are calculated. Now when you apply a DC supply, as per our assumption, a sinusoidally distributed flux or MMF will be produced, and the peak of this MMF will be along the axis of phase A. Similarly, if we energize phase B winding, then the equation is given like this. So the phase B winding will have the same magnitude given by NIB, but it is along the axis of phase B winding. So this is shown in the figure where the peak of the phase B winding is given along the axis of phase B, but it is sinusoidally distributed along the air gap periphery. Similarly, for phase C winding, if we energize it by a DC supply, so the equation of the MMF is given, and based on this the distribution of the MMF is given in the figure, where the peak of this MMF is lying along the axis of phase C and it is sinusoidally distributed along the air gap periphery. So if we combine the three results, if all the three phases are energized by a DC supply, then the MMF of the three phases can be given in the equation form like this, and they can be pictorially represented as given in the figure. Now let us see what will happen if you apply a sinusoidally varying current to the winding of any particular phase. So how the MMF of that phase will behave if you are applying a sinusoidally varying current. So let us consider phase A winding, and to this phase A winding a sinusoidally varying current which is shown in the figure is applied. Now mathematically the equation of MMF in phase A winding is given as n into small ia, where small ia is instantaneous current, and considering the sinusoidal distribution, this instantaneous current can be given as n into Im sine omega t. Now we can check the nature of the MMF distribution at different instants along the current waveform. So let us first consider the instant of omega t is equal to 0 degree. At omega t is equal to 0 degree, the sine omega t will be 0, and hence the MMF of phase A will be 0. Since MMF of phase A will be 0, so it can be shown on the theta axis in the figure. So the MMF distribution is shown along the theta axis, and its space phasor representation is shown with the dot. Now let us consider another instant of omega t is equal to 30 degree. At omega t is equal to 30 degree, sine omega t is 0.5, and therefore Fa is 0.5 NIM angle 0 degree. So we can say that the peak of the MMF phasor will be along the axis of phase A, and this peak is given by 0.5 n into Im. So therefore this MMF can be represented like this, where the waveform is distributed along the air gap periphery, and the same waveform can also be represented as the space phasor of the MMF, and this space phasor is directed along the axis of phase A, but it has half of the maximum magnitude. Now consider omega t is equal to 60 degree. At omega t is equal to 60 degree, sine 60 is 0.866, and therefore the magnitude of MMF is 0.866 n into Im. So depending upon this, the peak MMF will have a value of 0.866 NIM, and it will lie along the axis of phase A, but it is sinusoidally distributed along the air gap periphery. So this is shown in the figure, and the same thing can be represented by the space phasor with the length of the space phasor proportional to 0.866 NIM, and it is directed along the axis of phase A. Now consider omega t is equal to 90 degree. At this, sin omega t is 1, therefore Fa is n into Im, and this condition is represented in the figure MMF distribution and from the space phasor representation. Similarly, we can show the MMF distribution and space phasor representation for other angles. So at the angle difference of 30 degree, the MMF distribution and the space phasor distribution is shown. So at omega t is equal to 120 degree, we have this type of representation. Then at omega t is equal to 150 degree, we have this type of representation. Omega t is equal to 180 degree, the MMF is 0 again. At omega t is equal to 210 degree, the MMF will be negative and with half the maximum magnitude. So therefore the distribution of MMF will have the opposite polarity as compared to the previous case. So it can be shown in terms of the waveform like this, and in terms of the space phasor it can be shown opposite to the axis of phase A, but the length of this phasor is proportional to half of the maximum value. Then for the 2 omega t is equal to 240 degree, the MMF is shown like this. For omega t is equal to 270 degree, the MMF will have the maximum negative peak, and therefore it can be shown like this. And for omega t is equal to 300 degree, it is shown like this. Omega t is equal to 330 degree, it is shown like this. And finally at omega t is equal to 360 degree, the MMF will again be equal to 0. So this whole process can be represented with the help of the animation as shown now. From this animation you can see that the peak of the MMF phasor is always lying along the axis of phase A, but it is increasing from 0 value to the maximum value of NIM in the positive direction. Then it is decreasing from maximum positive value to 0. Then it is increasing in the negative direction, and then it is again decreasing from negative maximum peak to the 0 value as you are progressing from 0 degree to 360 degree on the current waveform. The same thing is shown in terms of the distribution of the MMF phasor, where the peak is proportional to the current magnitude. Now let us see what will happen if you will apply a three-phase balanced current to a three-phase balanced winding. For that, let us consider a three-phase balanced current where the magnitude of current in each phase is equal, and the three currents are phase there is a phase difference of 120 degree between the three current magnitudes. The MMF of the three currents, due to the three currents, it is given in the equations. Now similar to the previous case, again we will consider the different instants on the current waveform, and let us first take omega t is equal to 0 degree. With omega t is equal to 0 degree, FA will be 0, FB will be minus 0.866 NIM, and FC will be 0.866 NIM along the particular phase axis. Now the positive MMF will be along the particular phase axis, but the negative MMF will be along the opposite direction to a particular phase axis. So as you can see in the figure, the phase axes are shown with the dotted arrows. So the red dotted arrow is representing the axis of phase A, yellow dotted arrow is representing the axis of phase B, and blue dotted arrow is representing the axis of phase C. Since MMF along the phase A is 0, so FA is not shown in the diagram. The MMF along phase B is minus 0.866 NIM. So this will be drawn opposite to the axis of phase B, and it is shown like this. FC has the positive magnitude, so it will be drawn along the axis of phase C. Now the vector sum of these two MMFs will be the net MMF, and this is shown by the black arrow. Let us now consider the next instant, that is omega t is equal to 30 degree. For omega t is equal to 30 degree, the MMFs along A, B and C are shown like this, and if these are represented by considering the proper sign, the MMF of phase A is shown like this, MMF of phase B is shown like this, and MMF of phase C is shown like this. Now if we take the vector sum of all these three MMFs, the net MMF is shown along the FB. Now the next instant is 60 degree. At omega t is equal to 60 degree, the MMFs are shown like this, And with these MMFs, these can be drawn as the space phasor representation with F net shown as in the figure. Next instant is omega t is equal to 90 degree. So at omega t is equal to 90 degree, Fa is NIM angle 0, Fp is minus 0.5 NIM angle minus 120, and Fc is minus 0.5 NIM angle 120. So in the space phasor representation, these can be shown like this. So if we take the vector sum of these three MMFs, the net MMF will be along the axis of phase A. So you can see here, when we have moved from 0 degree to 90 degree along the current waveform, the F net, that is the net MMF, has moved in the clockwise direction from the vertical position to the horizontal position along the axis of phase A. So in a two-pole machine, the amount by which we have progressed along the current waveform in a similar by the same amount, the MMF phasor has rotated in the clockwise direction. Now we can represent the direction of the net MMF at subsequent instants on the current waveform. So at omega t is equal to 120 degree, these are the MMF of different phases, and these can be shown like this. Omega t is equal to 150 degree, we have MMF phasors like this, and these can be shown on the diagram like this with F net along Fc. At omega t is equal to 180 degree, the MMF magnitudes, these are shown like this, and on the space phasor representation they can be drawn like this. Now the F net is pointing in the opposite direction to that of when omega t was equal to 0 degree. Now if we move further at 210 degree, the FA, BFC are shown like this, and the space phasor representation is shown like this. Then we move further at 240 degree, then FA, BFC are shown, and the space phasor representation is shown in the figure. Then at 270 degree, FA, BFC are shown like this, and their space phasor representation is shown as in the figure, and now it is lying in the direction opposite to that of the axis of phase A winding. Now at omega t is equal to 300 degree, again we can represent FA, FB, FC and the net MMF like this. At 330 degree it is shown like this, and the space phasor representation is given like this. And finally at 360 degree, again FA, FB, FC, they have the same value as that at omega t is equal to 0 degree, and similarly the space phasor representation is also same as that of the omega t is equal to 0 degree. Now this whole process, the movement from omega t is equal to 0 to 360, this is shown with the help of this animation. As you can see in the animation, as you are moving along the current waveform with an angle of 30 degree, the net MMF is rotating in the clockwise direction by an angle of 30 degree. This is true for a two-pole machine. If you have higher number of poles, this movement will be slower. Second thing is, if you want to change the direction of rotation of the F net, you will have to change the phase sequence. That means after energizing phase A, you will have to energize phase C, and after that you will have to energize phase B. So phase C current will lag behind the phase A current by an angle of 120 degree, and phase B current will lag behind the phase C current by an angle of 120 degree. So if you have that condition, then the MMF waveform will rotate in the opposite direction, that is in the counterclockwise direction. Now In the previous analysis, we have seen the nature of the MMF waveform, but we don't know what is the magnitude of the waveform and what is the speed of rotation of the waveform. So for that, we will have to do the quantitative analysis. So for quantitative analysis, the mathematical representation of different MMFs is given like this. The instantaneous current IA, IB and IC, these can be given like this as a function of omega t. And if you substitute IA, IB, IC in the above equation, the MMFs can be written like this. Now the MMF is the summation of the three phase MMFs FA, FB, FC. And if you substitute the values of FA, FB, FC, Fnet can be written like this. Now in this equation, NIM can be taken as common. So you have the expression like this. Now in this, what we can do, we can represent the polar form of one angle 0 or one angle minus 120 degree or one angle 120 degree to rectangular form, and we can separate the real and imaginary components. So now we have converted the polar representation of the axis to rectangular form, and then we can separate the real and imaginary part of the different components, and then we can separate the real and imaginary part of all the components. We can take it together. Now in the real part, you can see that there are two portions. One is 1.5 sine omega t, other one is minus 0.5 into sine omega t plus sine omega t minus 120 plus sine omega t plus 120. So you can see that these are three sinusoidal terms which are at a phase difference of 120 degree. And from the mathematics, we know that when you have three sinusoidal terms which are phase displaced by 120 degree, then their summation is always equal to 0. So if you substitute 0 in this, this can be written like this. Now we can apply the trigonometric identity to the term in the bracket sine omega t minus 120 minus sine omega t plus 120. So if you apply a trigonometric identity, it can be written like this, where you are representing that term as a multiplication of a cosine and sine term. If you simplify this, the Fnet can be written as, the imaginary component can be written as minus j root 3 by 2 into 2 cos omega t sine minus 120 degree. Now we can substitute the value of sine minus 120 degree, and this is equal to minus root 3 by 2. And if we simplify it further, Fnet can simply be written as n into Im into 1.5 sine omega t plus j 1.5 cos omega t, and finally it can be written as 1.5 nim sine omega t plus j cos omega t. Now what we can do, we can convert it to a polar form, because in polar form we will have the magnitude of the MMF as well as the direction of the MMF space phasor. So to convert it to polar form, its magnitude can be calculated like this. So the magnitude of the MMF phasor, this is 1.5 n into Im, and its angle is tan inverse imaginary component divided by real component. So theta f is equal to 90 degree minus omega t. If you combine these two things together, Fnet can be written as 1.5 n into Im angle 90 degree minus omega t. So this is a mathematical expression representing the net MMF. So here you can see that the magnitude of the Fnet is equal to 1.5 n into Im, and the direction of this phasor is given by 90 degree minus omega t. If you put omega t is equal to 0, then this direction will be 90 degree with respect to the phase A axis, which is taken as a reference, and that is also true from the qualitative analysis that we have done earlier. So next you can see summary of the phasor position, MMF phasor position at different angles on the current waveform. So with this, you know what is the magnitude of the MMF phasor, but we still don't know what is the speed of this rotating space MMF phasor. So to know the rotating speed, let us summarize this thing. So what we have, when one cycle of the current is completed on the current waveform, you have one rotation completed by the MMF phasor, and this is true if you have a two-pole machine. But for a three-pole machine, for one cycle of the on the current waveform, you have 2 by p revolutions of the MMF space phasor. So an MMF space phasor is rotating by 2 by p revolutions for one cycle of current. For f cycles of current per second, it will rotate by 2 by p into f revolutions, and in 1 minute it will rotate by 2 by p into f into 60 revolutions, and this is effectively equal to 120 f by p. So 120 f by p is nothing but the speed of rotation of the MMF space phasor, and this speed is also called, is defined as synchronous speed, and it is denoted as ns. So this is a very important term, and in the subsequent lectures you will see the importance of this term. So you can see from the expression that synchronous speed is directly proportional to frequency, and it is inversely proportional to number of poles. So if you change the number of poles, you can change the speed of rotation of the magnetic field. So in Indian scenario, let us say the frequency is 50 Hertz, then the maximum speed is possible corresponding to minimum number of poles, and the minimum number of poles can be 2. So with 2 poles, the speed of rotation will come out to be 3000 rpm. Similarly, for 4 pole machine, the speed of rotation of the magnetic field will come out to be 1500 rpm, and for 8 pole machine it will come out to be 750 rpm. With this, we have completed the analysis of the rotating magnetic field, and we have calculated the magnitude of the rotating magnetic field as well as the speed of rotation of the magnetic field. Now you will see that this concept will be very helpful in the further analysis of three-phase induction motor. So if you like the video, please like this video and press the bell icon. Please subscribe this channel and share with your friends and colleagues. Thank you.